Differential calculus is a branch of calculus. It deals with rates of change. The rate of change of a function is called its derivative. The derivative tells us how much a function's output changes when we make a small change in its input. We can visualize the derivative as the slope of a curve at a specific point. Differential calculus has many applications. For example, we use it to find the maximum or minimum values of functions. We use it to model the motion of objects. We also use it to solve optimization problems. One fundamental concept in differential calculus is the limit. The limit of a function describes its behavior as the input approaches a particular value. Understanding limits is crucial for defining the derivative. The derivative is the limit of the difference quotient as the change in the input approaches zero. Differential calculus is a powerful tool that helps us understand how things change. It is a fundamental subject in mathematics, physics, engineering, and many other fields. Successive differentiation is the process of finding higher-order derivatives of a function. The first derivative of a function f of x is denoted by f prime of x. The second derivative is the derivative of the first derivative, denoted by f double prime of x. We can continue this process to find higher-order derivatives, such as the third derivative, f triple prime of x, the fourth derivative, f quadruple prime of x, and so on. Each higher-order derivative provides information about the original function. The second derivative, for instance, tells us about the concavity of the function. It helps us determine whether the function is concave up or concave down at a particular point. For example, consider the function f of x equals x cubed. The first derivative is f prime of x equals 3x squared. The second derivative is f double prime of x equals 6x. The third derivative is f triple prime of x equals 6, and all higher-order derivatives are 0. Successive differentiation has applications in many areas. These areas include physics, engineering, and economics. It helps us analyze the motion of objects, design structures, and model economic phenomena. Leibnitz's theorem is a formula for finding the nth derivative of the product of two functions. This theorem simplifies the process of finding higher-order derivatives of products. It expresses the nth derivative as a sum of terms. Each term involves a combination of derivatives of the two original functions. The formula uses binomial coefficients to determine the coefficients of each term. This theorem is particularly useful when dealing with complicated functions where directly applying the product rule repeatedly can be cumbersome. Leibniz's theorem is a valuable tool in calculus and other areas of mathematics. It is named after the mathematician Gottfried Wilhelm Leibniz, who is credited with its discovery. It has applications in areas such as differential equations and mathematical physics. Rolle's theorem is a fundamental theorem in calculus. It states that if a function is continuous on a closed interval ab and differentiable on the open interval ab, and if f of a equals f of b, then there exists at least one point c in the open interval ab, such that f prime of c equals 0. In simpler terms, Rolle's theorem tells us that if a function has the same value at 2 points and is smooth between those points, then there must be at least one point between them where the derivative of the function is 0. Geometrically, this means that the tangent line to the graph of the function at that point is horizontal. For example, consider the function f of x equals x squared minus 2x on the interval 0, 2. We can see that f of 0 equals f of 2 equals 0. The function is also continuous and differentiable on the interval. Therefore, by Rolle's theorem, there must be at least one point c in the interval 0, 2 such that f prime of c equals 0. Section 5. Mean value theorem. The mean value theorem is an extension of Rolle's theorem. It states that if a function is continuous on a closed interval, ab, and differentiable on the open interval, ab, then there exists at least one point c in the open interval, ab, such that fc equals fb minus fa divided by b minus a. This theorem has several important implications. It tells us that there exists a point where the instantaneous rate of change, or the derivative of the function, is equal to the average rate of change over the interval. In other words, at some point within the interval, the function's slope matches the slope of the second line connecting the endpoints of the interval. The mean value theorem has numerous applications. It is used in proving other important calculus theorems, such as Taylor's theorem. It is also essential for understanding the behavior of functions and for solving optimization problems. Section 6. Taylor's and Maclaurin's theorem. Taylor's theorem and Maclaurin's theorem are fundamental theorems in calculus. They deal with approximating functions using polynomials. Taylor's theorem provides a way to represent a function as an infinite sum of terms. These terms are calculated from the function's derivatives at a particular point. The theorem states that for a function f of x that is sufficiently smooth, we can write it as fx equals fa plus fa x minus a plus fa divided by 2 factorial x minus a squared plus, and so on, where fa, and so on are the function's derivatives evaluated at the point a. The term x minus a represents the distance from the point of approximation, a, to the point where we want to evaluate the function, or x. Maclaurin's theorem is a special case of Taylor's theorem where the point of approximation is a equals 0. In this case, the Taylor series simplifies to fx equals f0 plus f0x plus f0 divided by 2 factorials squared plus. These theorems are powerful tools for approximating functions and understanding their behavior. They have applications in various fields, including physics, engineering, and computer science. Section 7. L'Hospital's rule. L'Hospital's rule is a powerful tool for evaluating limits involving indeterminate forms. Indeterminate forms are expressions like 0 divided by 0 or infinity divided by infinity, where the limit is not immediately obvious. L'Hospital's rule allows us to evaluate these limits by taking the derivative of the numerator and the denominator separately. The rule states that if we have a limit of the form lim x approaches a of fx divided by gx, where both fx and gx approach 0 or infinity as x approaches a, then lim x approaches a of fx divided by gx equals lim x approaches a of fx divided by gx, provided the limit on the right-hand side exists or is infinite. L'Hospital's rule can be applied repeatedly if necessary, as long as the conditions for its application are met. This rule is particularly helpful when dealing with complicated functions, or when other limit evaluation techniques fail. It simplifies the process and allows us to determine the limit more easily. Section 8. Conclusion. Differential calculus is a foundational branch of mathematics that explores rates of change and function behavior. Understanding concepts like derivatives, limits, and their applications is crucial for comprehending how quantities change in relation to each other. Through successive differentiation, we can gain insights into higher-order derivatives and their significance in analyzing function properties. Theorems like Rolle's theorem and the mean value theorem provide powerful tools for analyzing function behavior over intervals. They guarantee the existence of points where derivatives exhibit specific characteristics, offering valuable insights into the function's graph and properties. Taylor's and Maclaurin's theorems provide a way to approximate functions using polynomials, enabling us to represent complex functions with simpler expressions. L'Hospital's rule helps us navigate the challenges of indeterminate forms, allowing us to evaluate limits that initially appear unsolvable. Mastering these concepts and techniques empowers us to tackle complex problems in various fields, from physics and engineering to economics and computer science. Differential calculus provides the tools for modeling real-world phenomena, analyzing data, and making informed decisions based on quantitative insights.